the water in your drink is radioactive. The banana in your bag too. And we are constantly bombarded by radiation from cosmic, outer space and our atmosphere. So how does that make you feel? Do you like that? I love radioactivity. It's a very unpopular opinion for some reason. But today I would like to change that. I want to convince you that radioactivity is actually awesome. Just think of it. Everyone knows radioactivity is used in medicine for diagnosis and treatment. It's used in archaeology, in history, to do radio dating, to get the age of ancient artifacts or woods. But even in the car industry, some manufacturers are using it to estimate the efficiency of motor oil in a car engine. Amazing, right? Radioactivity can do so much. I'm not working on any of these things. Yeah? These were just examples. I'm an astroparticle physicist and I'm working on something much cooler. I'm part of an international collaboration and we're building an experiment to detect one specific nuclear process, one specific nuclear decay. It has a complicated name. It's called neutrinoless double beta decay, and I will tell you what it is if you have an hour of time. But it's super rare decay for today, yeah? And when I say super rare, I really mean super rare. So if you give me one atom of the substance which we are investigating, I can tell it will not decay in 10 to the 26 years. So 10 to the 26 years is a lot. The current age of the universe is around some 13 billion years, so 13 times 10 to the 9. So you take that times a billion and then times another 10 million and you're there. It's a freakishly lot. So how would we ever think to be able to detect it? Yeah, but that's what we scientists are for, right? We do impossible things on a daily basis. That's our job. So yeah, I mean, the general idea is you just gather a lot of material. Yeah, we gather 1,000 kilograms of this amazingly expensive isotope from taxpayers' money, but yeah. And then we build detectors out of it. We build semiconductor germanium detectors out of it. And the hypothesis is that if this decay exists, well, one of the atoms of the detector should actually decay. It should emit 2 electrons. And then we can measure the energy of these electrons, and then we would know, yes, we have found this decay. But there is a problem. Your beer is still radioactive. And your banana too, and actually quite a lot. A typical banana has a radioactivity of about 15 decays per second. So, of course, in our daily life, it doesn't matter at all, yeah, if you eat 1 or 10,000 bananas a day. But for me, it matters a lot. Because if you have an isotope with a half-life of 10 to the 26 years, if you do the math, it means that in our experiment with 1,000 kilograms, we will have, in 10 years of measurement time, 2 decays. So don't go near our lab with bananas or water. Or even air in that sense. So it's a bit of a problem. And of course, we will solve this. We're scientists, right? So we go, first of all, we go underneath the mountain, some 1 or 2 kilometers underground because of cosmic radiation. Yeah, radiation is coming from the top, so we go down. Okay, check. Then we need to shield from the mountain itself because everything is radioactive on this planet, literally everything. So we build a tank, a steel tank. We try to find steel which is not as radioactive. And then we get some super pure water and we put it also in and we use it as a barrier, just as a passive barrier, as a wall to shield from outside radiation. And then in the middle we put our experiment. And then we turn it on, 1,000 kilograms of germanium detectors, and we see, bam, 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 bam. Oh my God, so many events, so many signals. Yeah, no way any of this can be really the super rare decay. It's just too much. And this is where my personal work starts, because you can only do so much with barriers. At some point you have to do particle identification, which means that I care about which particle or which radioactive decay is producing what kind of signals. And there is many methods you can use to do this, yeah. I'm working on pulse shape discrimination. And a pulse is what the detector sees. It's very easy. Usually it's just a voltage over time measurement, and I drew this myself. Yeah. And there is many different kinds of pulses. Yeah, this is one, and then there is that, and the shape of these pulses is the pulse shape, and it depends on the type of radiation or the type of decay. So if I know what pulse shape I have, I can tell you what decay it was. So discrimination just means to distinguish, to tell apart. That's just a physicist's term. Yeah. So we care about the difference between these two pulses, and we have a method we use to do this automatically, because we have to do this, of course, 1,000,000 times or so to analyze our experiment. We cannot do it ourselves by hand. But there is other pulses as well, which look like this. Yeah. And now if the left one is a super rare decay, which we want to measure, and the right one is just some banana decaying, it will be super difficult to distinguish. There is a small difference. If you have good eyes, you will see the right pulse is a little bit slower. It has something to do with the transition layer in the germanium detector, another 1-hour conversation you can have with me. But in the end, we have a method, but we just didn't know how good it was. So my professor asked me, can you find that out? And I said, yeah, I mean, I have a couple of other projects, and I have a student and lecturers and blah, 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 but he's my professor, so what can I say? Of course, yes. So we worked on it. There were a lot of other people involved as well. You cannot do something like this alone, and it took us a whole year. But then finally we found out, yes, actually we can discriminate between these two pulses, and the error rate is super low. It's just 0.38%, yes. So super cool. Now we know that if we detect this decay, we actually know it was the decay we're looking for, and not just some random water bottle some student forgot in the lab because they forgot. And now you may be wondering, so why do I care so much about this decay? Yeah, it's just some random decay happening all the time. Yeah. This decay is connected with everything in the universe. Yeah. For the experts, it's connected to the mass of neutrinos. Yeah. We will know why they have mass and what their mass is. But it's also connected to one very simple question. Why are we here? Why is there more matter than antimatter in the universe? Every astrophysicist will tell you, yeah, we should see a lot of antimatter out there. There should be galaxies and superclusters full of antimatter. But there aren't. There is some asymmetry. This is the famous matter-antimatter asymmetry. And if we find this super rare decay, neutrinoless double beta decay, we will know why there is more matter than antimatter. So next time someone complains about radioactivity, nuclear waste, nuclear reactors, and blah, 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 you know what to say. It's not only about these things, yeah? Radioactivity is connected to fundamental physics. It's exciting, it's awesome. Thank you.
Christoph Vogl. Christoph Vogl, ladies and gentlemen, from the Origins Cluster.